Today I am going to start a new section of classical mechanics. Here I will talk about Hamiltonian formulation of mechanics. So first of all, in this lecture I will talk about the introduction. And in introduction I will talk about canonical, conjugate momentum, cyclic coordinates and ignorable coordinates, and these are very important for the formulation of mechanics in terms of Hamiltonian. So in the earlier lecture, I talked about Lagrangian formulation in terms of generalized coordinates, but here I will discuss a new approach, and that new approach is known as Hamiltonian approach. Right. So, but first of all, I will discuss new concepts. Like cyclic coordinate, conjugate momentum, canonical conjugate pair, Sometimes this conjugate momentum is known as canonical conjugate momentum, right? And the cyclic coordinate is sometimes also known as ignorable coordinate. So these are the things about which I will talk about here in this lecture. So for this, let us consider a Lagrangian. Say L is the Lagrangian, and it is generally denoted by Q1, Q2, and so on, QR, and so on. Then Q1 dot, Q2 dot, and so on, QR dot comma T. Right, this is the Lagrangian, and where these QR are the generalized coordinates. QR, where value of R will become 1 to n, and this represents generalized coordinate. Right, this is all about it. So here one thing is very interesting. Here Q represents the generalized coordinate, and Q dot basically represented generalized velocity. And when velocity multiplied by mass, then this will become the momentum. So a idea will came up in our mind that why not to represent this Q dot by the momentum. So another interesting thing which we have to keep in mind, if we define a term, means if I take a derivative of Lagrangian in terms of velocity or generalized velocity, then this will basically equivalent to conjugate momentum. This is equivalent to conjugate momentum. So we call this conjugate momentum corresponding to generalized coordinate. How idea will come up in our mind, since we know that this Lagrangian is kinetic energy minus potential energy, and let us call kinetic energy is equal to half mv square, and we know that potential is a function of generally function of r, and this dry dt is basically v. So I can express it as the this L is equal to half minus PR, so it is 1 by 2 mr dot square minus BR. But if I take derivative of this L with respect to velocity, then it is 1 by 2 mr dot minus VR, and this will cancel out with it, so it is mr dot, or I call it as mb, and it is basically the momentum. So this gives me the idea about it, right? Because in general this is basically depending upon r, so its differential will be comes out to be 0, and its value will be 0, right? Its derivative will be 0. That's why it is a momentum. It is equivalent to momentum. So that means it gives us idea to express Lagrangian in terms of momentum. So now the pair, because PR is somehow relating to QR, so this pair QR comma PR is called canonical conjugate pair of variables, right? So this is known as canonical conjugate pair of this. Now let us generalize the idea, and this conjugate momentum is sometimes known as canonical conjugate momentum, right? Sometimes, or in most of the texts it is also known as canonical conjugate momentum. Now let me generalize this idea. Let us understand this idea with the help of some examples. So let us take few examples. To appreciate the idea of canonical momentum. As we know that Lagrangian is T minus V, it is also discussed, but now I am taking it's a motion of one dimension. So for one-dimensional motion, it is the kinetic energy along x-axis, and it is the potential at a particular point, particular position x. Now, if I take curly L over curly x dot, then it can be written as mx dot, because its differential will be 0, partial derivative, and this is px, and this is basically the linear momentum. Thus, linear momentum is canonical conjugate momentum corresponding to x. This is a very simple example, as I talked about in the earlier slide also. So now let us take another example. Let me represent Lyt minus b, and it is half ml square theta dot square. It's rotational motion, and potential is also depending upon theta. Now if I take curly L over curly theta dot, then its derivative comes out to be ml square theta dot, and it is nothing but it is the angular momentum. And this is represented by p theta. Now p theta is basically canonical conjugate momentum corresponding to angular displacement, right? So angular momentum is the canonical conjugate momentum, means I can say that angular momentum is canonical conjugate momentum corresponding to angular displacement. That is theta. So that means theta comma p theta, they will form the canonical conjugate pairs. Canonical conjugate pairs, right? So this is all about it. So now let me generalize this idea of canonical conjugate momentum. So generalization of idea of canonical conjugate momentum. Let us understand it now. So in terms of generalized coordinates, kinetic energy and potential energy can be written as that T is equal to half, this I have discussed in the earlier lectures, Aij Qi dot and Qj dot. Here Aij is equal to Aji, this we have to keep in mind, and the potential can be written as 1 by 2, it's basically the function of potential may be anything, so it is Q1, Q2 and so on Qn, right? Very simple idea. Now Lagrangian is defined as, this Lagrangian is equal to T minus P, and let me put their values here. So if I put their values, it is 1 by 2 Aij Qi dot Qj dot plus Pq1, Q2 and so on Qn, and here summation over Ij, and let me open it up, this summation. So it is 1 by 2, it's just outside, summation over j, and I will open the summation over I, so it can be written as Q1j, sorry, not Q1j, but it is A1j Q1 dot Qj dot plus A2j Q2 dot Qj dot plus and so on Arj Qj Qr QR dot and QJ dot and so on, plus B Q1, Q2 and so on Qn. Now, if I take its differential with respect to partial derivative of the Lagrangian with respect to QR dot. So if I take its derivative with respect to R, no term containing QR is there, QR dot. So that means its differential will be 0, it will be 0, but its derivative will be 1, keeping these two constants, and its derivative will also be 0. So it means it comes out to be ARJ QJ dot, right? And rest of the terms will become 0 and its derivative will also, it is also equivalent to PR. So this is known as, this PR is the canonical conjugate momentum corresponding to QR. So that means QR comma PR, they form the canonical conjugate pair. Right? Now, let us assume that, or let us consider a situation when L does not depend on the particular coordinate. Means if for a particular coordinate, generalized coordinate QR, out of so many large number of, because we are having a Q1, Q2 and so on Qn, out of which it does not depend upon QR, means particular coordinate, then I can say that its differential with this partial derivative with respect to QR is always 0, because L does not depend on QR. If I consider this case, then according to Lagrange's equation of motion, let me call that equation. So it is d upon dt curly L over curly QR dot minus curly L over curly QR. It is always equal to 0. But as I know that its value will be 0, so if I put it here, then what I am getting? I am getting d upon dt curly L over curly QR dot, it's equal to 0. But what is it? It is the canonical momentum. It is PR. So that means d upon dt PR is equal to 0, which implies that PR is equal to constant of motion. Right? So let me summarize this result. That if Lagrangian is cyclic, in one of its, let me do one thing. Yeah. If I say that for a particular QR Lagrangian will be 0, that means QR is a cyclic. this we have to keep in mind. So let me summarize the result keeping this in mind. Thus, if Lagrangian is cyclic in one of its coordinate variable, say here QR, here, that is for this curly L over curly QR is equal to 0. So if Lagrangian is cyclic in one of its coordinate variable, then its corresponding canonical conjugate momentum is called constant of motion, and such a coordinate QR is also called ignorable coordinates. So what we did, we tried to write down the things as earlier they are in terms of velocity. Now here we have tried to express the things in terms of not velocity but in terms of momentum. So this is all about today's lecture, and in the next lecture I will talk about Lagrangian transformations and I will try to define the Hamiltonian. So that's all for this lecture.